Hey guys, Mr. Betts here. I want to talk about a process that we're going to use to solve differential equations called separation of variables. For now, we're going to talk specifically about general solutions. This should be a term that is familiar to you, but in case it's not, just a quick refresher. A general solution is a solution to a differential equation that includes all possible functions that have that differential equation as a derivative. Or in other words, we could take the derivative of the function and plug it in for f prime of x. That equation would be true. Notice that the general solution here has this constant of integration in it. So no matter what that c is, when we take the derivative of this function, that the derivative of the plus c goes away, and so f prime of x is going to be 2x. So it's a family of solutions, and I say a family because it's a whole bunch of solutions, infinitely many of them actually, that all have the same derivative. Um, so if we have a differential equation where the derivative is defined entirely in terms of the independent variable, I know that's a lot of kind of big words there, but as long as x is the only variable in the differential equation, or t in this case, because that's the independent variable, it's a pretty easy or straightforward thing to do. We just use anti-differentiation. So the first one here, f of x, is just going to be sine of x plus c, because the derivative of sine of x is cosine of x. On this one, we're going to have y equals arctangent of x plus c. Last one, we're going to have a equals t cubed minus 5t plus c. So all of these, we're just taking the antiderivative of the expression. However, we're going to start seeing problems where we're going to have x's and y's mixed together. This may look familiar. This is the sort of thing that happened when we took derivatives using implicit differentiation. We would get derivatives that had x's and y's mixed together. So when we do have this mixture, we're going to have to use a different process. And that process we're going to use is called separation of variables. And the basic idea is that we need to separate x's from y's. So we're going to get everything that has to do with a y on one side and everything that has to do with an x on the other side. So I want to go through the process first, and then I'll go through that example that I just had on the screen there to show you how it's going to work. And then I would encourage you to watch the other video with more examples. So the idea is we're going to separate variables. So we're going to get all of one variable on one side, all of the other variable on the other. One key thing is that the differentials, so the dx, the dy, the d theta, the dt, whatever those differentials are, they need to be multiplied by the entire expression on the respective sides. So on one side, we'll have an expression with y's in it and multiplied by dy. On the other side, we'll have an expression with x's in it multiplied by dx. Then we're going to take the antiderivative of each side. And with the differentials on there, we take the antiderivative with respect to that differential. And then we solve for y. I do want to point out that in the second step, when we take the antiderivative, we only need the constant of integration once, even though we're taking two antiderivatives. And the reason is if we have a plus c on both sides, those plus c's will probably be different numbers. They don't necessarily have to be. But the difference between those two constants is itself a constant. So I'll explain that when I go through that example. But then ultimately, when we solve for y, we want to get y by itself, and we will have that constant of integration somewhere in that expression. So looking at this one right here, the first thing we're going to do is separate variables. And I usually like to start that process by multiplying by the differential in the denominator so that we know what goes on what side. So this isn't necessarily something that I would write as a completely separate step, but I'm going to in this example. So we have 2x plus 1 over cosine of y, and then multiply dx, and we get that over there. So anything with an x in it needs to be on the right side. Anything with a y in it needs to be on the left side. So we're going to multiply by the cosine of y and get that. So just cleaning that up, and this is what I would do it all in one step if I can. We're going to get cosine, let me try that again, cosine of y times dy equals 2x plus 1, and that entire quantity is multiplied by dx. Okay, so notice that we multiplied the entire right side by dx, so we do need to put this in parentheses here. Now, at this point, we can take the antiderivative on each side. So the antiderivative is an operator. It's just like if we would add the same thing to both sides or divide by the same thing on both sides, we're taking the antiderivative on both sides. So we take the derivative of sine of y to get cosine of y. For now, I'm going to write in here a plus c, and I'm going to call it c sub y because it's on the y side. And then on the other side, the antiderivative is going to be x squared plus x. And then also, when we take an antiderivative, we're going to have a plus c. I'm going to put c sub x. So those are going to be two different constants. And what I was mentioning earlier is that if I subtract the c sub y from both sides, this right here, a constant minus another constant, is itself a constant. So what we're going to do here is we're just going to put a plus c on one side, and that takes care of the constant of integration for both of our antiderivatives. Now, the last thing we want to do to get a general solution here is to get y by itself. So we are going to take the arc sine on both sides. So we have y equals the arc sine of x squared plus x plus c. And notice that that constant of integration doesn't come at the end here, but it's actually embedded in the expression, and that happens when we solve for y. So oftentimes when we get a general solution, there's going to be a constant of integration in there, but it's going to be mixed in with the other stuff, and it's important that we have it in the right place. So again, I'm going to put these steps on here, and I went through all these steps in that example. So we separate variables, we take the antiderivative of both sides, and then we solve for y.